the number of distinguishable permutations of a set containing 2 or more indistinguishable elements is given by this formula. In factorial, that's just the number of items there are, divided by in 1 factorial, in 2 factorial, ... in r factorial. Now, that formula looks really, really complicated, but it's really not that bad, okay? Essentially, what you're doing is dividing by the number of repeats, okay? Indistinguishable elements are items that look exactly the same, okay? So if you look at example 8 says, how many ways are there to arrange the letters of the word? Well, we've already done a problem like that. I see 1, 2, 3, 4, 5, 6 letters. And so, it's like a blanks problem where you could do a factorial. The answer is going to be 6 factorial, okay? But we can use the distinguishable permutations formula if we want to, and it would work something like this. Since there are 6 letters total, that would be the numerator, 6 factorial. Okay? But then on the numerator, you have to go through each of the individual pieces, okay? So see how there's 1 O, and there's 1 R, and there's 1 A, and there's 1 N, and there's 1 G, and there's 1 E. And so we're just dividing by 1, which is kind of silly. Okay, it's kind of silly because that's just going to equal 6 factorial. And 6 factorial is 720. So it was kind of silly to use the indistinguishable permutations formula there. But I just wanted to show you that it was possible. It would have been better if you just recognized that's 6 factorial. We get to a word like Mississippi, and that's going to be a little bit more appropriate, I think. So you have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 letters total. If they were all different, the answer would just be whatever 11 factorial is, okay? But since there are repeats, I'm going to divide by the repeats, okay? So what I would do is the ones, it's kind of silly to divide by 1. So I'm going to kind of skip the ones and only divide by the ones that have repeats, or, how'd they say it, indistinguishable elements. See how there are 4 I's? 1, 2, 3, 4 I's. I'm going to divide by 4 factorial. Basically, what that's doing is figuring out the ways of shuffling those I's. If you shuffled those I's, nobody would know because they're indistinguishable. So look at the S's. I see 1, 2, 3, 4 S's. So I'm going to divide by 4 factorial for the S's. And then I also see a couple of P's there. 2 P's. Now, if you notice the numbers on the bottom add up to 10, you could throw on the 1 factorial for the M. You might want to do that just so it adds up to 11. Notice the numbers on the bottom add up to 11, which was the total number. So I usually don't put the 1s on there. I'll usually just put the repeats. We need to calculate this. Be very, very careful because I know a lot of students will try to type it in on a calculator and will mess it up. If you use a calculator, when you divide it, you must use parentheses so that it divides by all of these things. If you don't put that in parentheses, it's not going to work, trust me. So I've got 11 factorial divided by all of that other stuff, 4 factorial, 4 factorial, 2 factorial. I get 34,650. There are 34,650 ways to shuffle those letters differently. So let's look at bookworm. Bookworm is the same thing. I see 8 total letters, and we're going to divide by the repeats. There's only 1 B, and there's only 1 K, and there's only 1 W, and there's only 1 R, and there's only 1 M. I'm not even going to look at those. I'm just going to divide by the 3 repeated O's. Okay, so again, what that means is there are 3 factorial ways of shuffling the O's. You'd never know it. If I shuffled those O's, you'd never know it because they're indistinguishable. We just need to divide 8 factorial by 3 factorial. We get 6720. Okay. Number 9. How many ways are there to line up the following playing cards? So notice some of those cards are the same. You see how there's several ace of hearts? You got a couple of 8 of spades and a couple of 5s. Okay, think about it this way. There's a 7 and a 10 and an ace and a 5 and an 8 and an ace and an 8 and an ace and a 5. This really is the same problem as the Mississippi problem. Okay, those aces are indistinguishable and those 5s are indistinguishable. If I switched them around, you'd never know if I switched 2 5s around. This is the exact same problem in disguise. So notice there are 1, 2, 3, 4, 5, 6, 7, 8, 9 playing cards. And we're going to divide off the repeats. So there's only 1 7, so don't worry about it. There's only 1 10. But I see 3 aces and 2 5s and 2 8s. So it's really the exact same problem. Now again, be careful on your calculator because when you divide, you must put it in parentheses. $15,120. Number 10. A student buys 3 Cokes, 2 Diet Cokes, and 2 Mountain Dews. She puts them in her fridge, planning to drink 1 a day for the next week. And how many ways can she arrange her drinks for the week? So notice those 3 Cokes are going to be indistinguishable. That's kind of your clue. How I like to do this problem is I like to write it out like this. There's 3 Cokes, there's 2 Diets, and there's 2 Mountain Dews. It's the same exact problem as the Mississippi problem. It's just disguised as a story problem. I see how many? 1, 2, 3, 4, 5, 6, 7. 7 letters total. Again, if they were all different, that would be your answer, 7 factorial. But since some of them are indistinguishable, we're going to divide by the number of ways of shuffling each of those different types of letters. Divide by 3 factorial, 2 factorial, 2 factorial. In parentheses, and we get 210.